Our next speaker is Tingjun Chen, who is the Nodal Networks Assistant Professor in the Electrical and Computer Engineering Department and also a secondary appointment in Computer Science at Duke University. He works on various projects cutting across networking, communication, sensing, and energy-efficient computer aspects of various networks, including wireless and mobile networks and optical and quantum. And he works on various things, including theoretical and experimental research. And now his upcoming talk, Scalable and Real-Time Baseband Processing Using Heterogeneous Compute Resources. Thank you.
All right, thanks for the introduction. Hello, everybody. My name is Tingjun Chen. I'm from Duke University. And today I'm going to talk about some of the work that we've been working on the past, I would say, 3 to 4 years on how do we actually leverage heterogeneous compute resources, including CPUs, GPUs, ASICs, to deal with perhaps the most computationally expensive tasks in 5G, 6G baseband processing, which is actually digital signal processing in the first layer, in the physical layer. I think, as Vijay already mentioned, virtualization has brought many benefits for future networks, right? So basically allows you to largely reduce the development cycle. You can actually make software-only updates to many of the problems that we are looking at, new features we plan to integrate into the system. And also these cloud-native scaling also would flavor software-centric upgrades and also multi-tenancy support. For example, can actually coexist machine learning AI workload alongside baseband processing if the GPU is found to be idle. And even CPUs and ASICs can do other stuff in parallel. So on the right-hand side, I show 3 typical L1 processing models for inline processing. For example, you can run everything in layer 1 on a single entity. This could be everything on CPU based on Intel's FlexRAM platform. This could be everything running on GPU based on NVIDIA's Aerial platform. And then this single entity has a single memory bus. And then all the DSP stages basically move data between each other through this same memory bus. And then there's also another popular model, which is look-aside acceleration, where you have an additional hardware accelerators sitting next to the main CPU. You can decide to partition the DSP tasks between different types of processing unit. You can, for example, put FFT, equalization, demodulation on CPU, which has its own memory. You can then offload several other stages of DSP into a nearby hardware accelerator. But in this case, the CPU and the hardware accelerator are actually using different memory, so it actually incurs additional memory movement between the 2 computing entities. And then example here is, for example, if you run, let's say, FlexRAM with ACC 100 support, you can actually run everything before LDPC decoding on the CPU, and you can choose to offload LDPC decoding to accelerator hardware. And then there's also a third paradigm emerging. Basically, you can actually use what we call hybrid acceleration, where you have both the CPU and hardware accelerator as part of the same platform. But these 2 entities actually share the same unified memory bus, right? Examples are Jetson Nano, Jetson Orion platform, which runs NVIDIA Sionna research kit, and many of the modern Grace Hopper series machines from NVIDIA also have this unified memory structure. So the problem we are looking at here is basically how do we trade off latency and power constraints when you're actually putting different DSP stages across different computing paradigms to make sure that you not only satisfy the very tight processing latency requirements in layer 1, but also you're actually using the minimum amount of resources in terms of compute, and also you're saving power when you're running this layer 1 processing over heterogeneous compute resources. So we started this problem about 3 years ago. So the first problem we looked at was basically using CPU plus ASIC. Right here we have Intel server-grade Xeon processor co-located with ACC 100 accelerator hardware from Intel. And then we look at the problem of baseband processing in the context of supporting FR2 cells, which have much shorter latency constraint compared to FR1 cells. So here, if you look at existing solutions optimized for layer 1 processing in FR1, if you scale everything to FR2, which has, for example, in this particular case, 8 times shorter latency deadline compared to FR1, then many of the software-only based solutions would fail because of the very tight latency constraints you get, especially when LDPC decoding start to prioritize and dominate the overall latency performance. So actually, we built a system called Savannah, which includes CPU processing and also offloading LDPC decoding tasks to a nearby hardware accelerator to not only reduce the processing latency for for FR2 cells, but also to be able to actually reduce the amount of reduce the power consumption when you're actually processing different types of cells, right? And then this integration was actually drawn on two key insights. The first one was that FR2 cells, you deal with many small matrix operations, but across very large number of subcarriers, you can design better ways to actually map the data processing vectors to the right memory architecture, and then which are most suitably to run on these AVX512 instruction sets. And then also we did a lot of profiling in terms of how these physical ASIC hardware can do in terms of supporting different types of modulation coding schemes when performing decoding tasks. How does the decoding throughput changes versus number of concurrent processing code blocks, and also compare that in terms of the throughput gain if you were to actually run LDPC decoding on a set of multi-core machines, right? And then based on all these observations, we designed a system that optimizes layer 1 processing for a single FR2 millimeter wave cell, in the sense that we can achieve significantly increased processing throughput, and also making sure that we choose the right amount of compute resources that leads to the least amount of energy when you're actually processing this cell. So in a nutshell, we tested on a server platform, and also we tested this with experimental FR2 hardware from IBM, and we showed that our system can support up to 2x2 MIMO 100 megahertz cell in FR2 latency deadline with a single CPU core and offloading LDPC decoding tasks to ASICs. And even in this case, we're reducing the power consumption by a factor of 2 comparing to, let's say, CPU-only based solutions, because in this particular case, LDPC decoding offloaded to ACC 100 is equivalent to using about 4 to 5 CPU cores, whereas the hardware ASIC accelerator actually consumes much less power compared to stacking up CPU cores for LDPC decoding. Right. So, and then we extend this effort to look at multi-cell processing. The problem here is actually very simple. You want to support heterogeneous processing of a pool of radio units with potentially heterogeneous configurations in terms of bandwidth, MIMO size, traffic load in both the time and frequency domain, as well as different levels of modulation coding schemes. And then if you are given a single server with a pool of CPU resources and a given number of, let's say, hardware accelerator cards, how do you design the optimum compute resource allocation strategy in a way that you not only guarantee the latency processing deadline for all the cells that a single server is serving, but also you're actually using the least amount of energy when you're processing those set of cells, right? It's kind of our problem setting. And we built a system called Nexus. Basically, we co-optimized software DSP running on Intel Xeon processor and LDPC decoding offloading to ACC hardware accelerator through virtual function implementations. We also designed power-aware compute resource allocation strategy to determine what is the best set of CPU cores and ACC virtual functions to be used to finish this entire L1 signal processing. And we show that through experimental implementation, a single server can support up to 16 cells with a total uplink data rate of about 5.4 gigabits per second, using only 16 CPU cores and one single ACC hardware accelerator, which is then virtualized into 16 virtualized functions. And also the whole system design, profiling, modeling methods are scalable to supporting larger number of servers serving an even larger number of cells, right? So to dive deep into how do we actually optimize heterogeneous compute resource for layer 1 processing. So here let's consider a cell configuration sigma, which composed of channel bandwidth. You can actually see the values here. We consider very channel bandwidth, a MIMO dimension, a time domain traffic load in terms of how many data symbols in one slot is occupied by actual uplink transmission, and also transmission bandwidth, and also different modulation coding index, right? And then, we consider the problem of resource allocation. If you are given, C number of CPU cores and V number of virtual functions, virtualized from different ACC 100 ASIC hard, how do you actually decide, how many CPU cores should be used for software-based processing, how many CPU cores should be used to interact with the hardware accelerator, because this is actually the Lucaside L1 processing model. And also, how do you actually allocate virtual function in a way that they can satisfy your layer 1 processing latency requirement? So we actually considered this, what we call the feasible compute resource allocation strategies based on how we understand the hardware accelerator would be able to work with a CPU cores in a machine. We considered this type of constraint, right? For example, every CPU core can be dedicated to either a software-only DSP or taking care of offloading LDPC decoding to hardware accelerators, or can do actually both tasks at the same time. And also you have to make sure that on the other side, every core responsible for ACC and LDPC offloading is mapped to a unique set of virtual functions virtualized from that ASIC card. And also every virtual function cannot be managed by more than one CPU core in order to prevent conflict from happening. So basically, if you actually formulate all these constraints, this becomes a combinatorial problem. If you actually have these constraints, you can actually compute how many possible resource allocation strategies are available for you to actually satisfy these, what we call feasibility constraint. Right? And then we also look at the power consumption perspective of this allocation. So here, our goal is to actually select the best allocation of compute resources such that we minimize the overall power consumption of the system when running a set of layer 1 processing tasks. So here you can basically consider this weighted power equation. You have this coefficient alpha 1, alpha 2, alpha 3 in front of the power consumption corresponding to the CPU cores responsible for software DSP, the CPU cores corresponding to handling offloading tasks to the ACC ASIC. And also, this ACC ASIC hardware can also incur a different amount of energy when running different number of virtual functions for LDPC decoding. So actually, we did a lot of experiments, right? We used Intel's performance counter monitor to monitor CPU power consumption. We use different methods to actually, clamp meter, try to measure the power consumption of this Intel ACC accelerator PCIe card, and then come up with this profile that tells you, how much power this ASIC card would consume with respect to different number of virtual functions running LDPC decoding tasks on these single ASIC hardware, right? So basically, we plug in this equation, you can formulate this power-aware optimization problem to select a number of resources in terms of CPU cores and virtual functions for your layer 1 processing tasks. However, the challenge here is actually, first of all, as we mentioned, right, we're actually searching through a very large configuration space. If you are given a, let's say 50-core server with, let's say, 2 ASIC cards, which can be virtualized into 32 virtual functions, you're actually searching through a very large configuration space. And secondly, the constraint here is not something that you can easily mathematically model, right? Because we're actually trying to satisfy the latency processing requirement to be shorter than, let's say, a 3-slot deadline, which is actually very difficult to map from, the resource you put in to the actual latency, and then there's also variance in terms of the actual latency during the processing framework. Right? So basically, we took the approach. We come up with a very comprehensive set of benchmarks. We vary in this particular case, we vary the cell configuration. Right? We consider 1 by 1 400 megahertz, 2 by 2 200 megahertz, 4 by 400 megahertz. We consider varying traffic load. I'm only showing 50% here and 100% here, and then we run through all these different configurations in terms of combining different numbers of CPU cores and virtualized functions to understand the power latency trade-off of a very big configuration space, right? And then if you draw this 3 TTI deadline here, you can basically find out the best strategy that satisfies the baseband processing latency requirement while consuming the least amount of power by looking through all these processing resource allocation strategies. And then, based on this empirical observation, we mainly focus on considering these 4 set of resource allocation strategies. The first one is CPU only. There's no virtual functions involved. You allow every CPU core to process the common PHY as well as the LDPC decoding implemented based on the FlexRAN decoder. We consider the second scheme where you allow one CPU core to deal with everything in the physical layer, including coordinating with a number of virtual functions, while the remaining CPU cores are completely focused on DSP processing before LDPC. You can also, to do something else, you can actually assign a dedicated CPU core just for handling all the virtual functions with respect to the ACC hardware, and then assigning the remaining CPU cores to do everything else except for the LDPC decoding. You can also have this complete hybrid mode where every single core can perform not only DSP in software, but also to handle the LDPC decoding offloading to eASIC hardware. Right? And then because of the very large configuration space, in order to actually have this map out between a set of compute resources and whether that set of compute resources can satisfy your latency processing requirement, we developed a random forest-based feasibility predictor that tells you, given the cell configuration as a function of bandwidth, MIMO size, traffic load, modulation coding scheme, and also given compute resource allocation strategy theta, we basically build this predictor that maps, the input, your selected strategy based on the cell configuration into a value that predicts the likelihood of that configuration being able to sustain the latency requirement under that cell configuration. And then we train this random forest based on massive profiling experiments, and then we show that it can actually predict very good how a given strategy can sustain the layer 1 processing even for unseen cell configurations. And then also we will compare this random forest mechanism with other machine learning based approaches. We show that random forest actually works pretty well in terms of mapping these two-dimensional resource allocation problem to a feasibility test to understand if baseband processing can be supported by the given set of compute resources. Right? And then we also extend this approach to support multi-cells. And then here we assume that there's non-overlapping resource allocation across the cells. And then we leverage what we learned from modeling and profiling a single cell. And then we build this power-aware and contention-aware latency adjustment to extend the latency modeling from a single cell into a multi-cell scenario. If the predicted cell it cannot meet the latency requirement, the scheduler will go to the next best configuration in terms of trading off the power efficiency versus the amount of compute resources being used. So here we show some examples of a single server equipped with a single ASIC decoder virtualized into 16 virtual functions. So basically, this is a 26-core machine with 16 virtual functions in a single server. We show that, for example, if you run 16 one-by-one CISO cell, right? You can basically assign a single CPU core for every cell, and then you also use the same CPU core to handle the virtual function offloading for that single cell, and this goes all the way up to 16 cells. Everything works well. And then now, if you want to start serving more complicated cells, for example, if you want to serve CISO 200 megahertz cells using the same strategy, then you actually figure out once it goes above 10 cells, all the memory contention and data movement between the CPUs actually start to create nonlinear effect in terms of the overall computing latency. That's why as you start to increase the number of cells to be served by the same server, you start to violate the latency deadline when you reach to more than 10 cells. And here, if you were to apply our scheduler, it basically will give you a different strategy to basically assign 2 more CPU cores in this case to handle the DSP stages, and then this can bring the processing latency down to below the 3 TTI deadline. And similar behaviors can be observed if you were to serve cells with different configurations. Right? And also we test this on heterogeneous cells. Right? For example, different colors here in each group basically shows a different cell configuration. We consider CISO 100 megahertz all the way up to 4x4 MIMO 100 megahertz, and then the right-hand side shows you the configurations of different combinations of CPU cores and the virtual functions being used to process every individual cell. And then here I put a number in terms of the total front-haul traffic based on split option 8 that is actually handled by the single server at the beginning of the layer 1 processing strategy. So we built this entire code base in C++, including a complete set of benchmarking tests. You can actually run this by yourself if there's interest. Overall, we built a system that supports heterogeneous multi-cell baseband processing. Although we are targeting in FR2 because of the tighter latency requirement, we believe that the way we model the system, we profile the system can also extend to FR1 and even FR3 cells with different amount of configurations. And then the key difference here would be here we are dealing with smaller dimensional MIMO, where software-based MIMO processing is not a big challenge. Whereas if you go to the large dimension MIMO, let's say massive MIMO in FR1, then it's going to incur a significant overhead in terms of software-based matrix inversion when you're calculating the MIMO matrices, right? And more recently, we take one more step to actually benchmark LDPC decoding performance across CPU, GPUs, and also ASIC platforms, right? This actually goes back to the 3 layer 1 processing models that we look at. We have the CPU-based only solution, where we look at FlexRAM-based LDPC decoding on a multi-core server. We have the look-aside approach, where we benchmark LDPC decoding solution on Intel's ACC100E ASIC, as well as we're running this aerial-based decoder on NVIDIA H200 and also RTX 3090 systems. And this is basically the decoding latency as a function of SNR on the x-axis and modulation coding scheme on the y-axis. And then based on these profiling results, you can get a much better sense of how different types of hardware are performing in terms of latency for these LDPC decoding tasks. And then one can perform very similar things, not only for LDPC, but also for other stages of your DSP pipeline to understand how do you actually trade off latency, power consumption in this layer 1 processing when you are incorporating different types of compute resources. Right? So that's kind of the new work. And then we're also open sourcing the code and also the way we build the benchmark and then the way we make all these energy latency trade-off results, right? And then this cannot be done with my group of students. Actually, many of them are here today. If you have any questions about the actual details, you can go to my students in that corner. They can actually tell you more about how do we build and test the systems. And then I'll stop here, and if there's any questions.
Based on your study so far, right? You also touched on this, the challenge of massive MIMO. Like how this trajectory may look like in, let's say, in the coming 1 to 3 years, when we see potentially using some of these platforms for instead of ASIC for building such systems.
Right. So I guess the challenge with ASIC is that we cannot really build an ASIC to actually handle, let's say, 256 antenna MIMO systems. But my guess is that's something we're actually working on now, is that we need a very comprehensive benchmark to understand the trade-offs between, let's say, CPU-based and GPU-based matrix operations in the context of 5G. Right? For example, if you are dealing with a 1,000 antenna system, then if you were to still use, let's say, Intel CPU to process your huge channel matrices, it may not be as good as if you throw everything on a GPU. There was actually a recent paper from NSDI 2025 that works at GPU-based L1. They actually augment on aerial and then look at performance in terms of using GPUs to handle, I think, up to 256 antennas in massive MIMO systems, right? I think in those type of systems, GPU will actually show larger benefit. And then if you were to do your CSI calculation in GPU, then you'd better do everything in GPU to avoid all the data movement between different compute domains, right? So that's why I think if you look at the entire L1 processing as a computational graph, then you don't want to switch between different platforms that frequently. I think that's why how do you actually think about the partition, where to move things to GPU, where to move things back to CPU. I think there's actually very big space, interesting problems that one can explore. Yeah. And I also want to mention power, right? So faster processing doesn't mean it's more power efficient, right? If you were to, let's say, use twice less power while increasing the latency by, let's say, 5%, right? That might be something worth considering if it still satisfies the product. That's why we're doing all these, what we call power-aware scheduling.
Thank you, Tingjun.